So we've considered a sample point, rho I star, theta j star, phi k star. Sample point that we'll say is here. We've got a volume increment around this thing defined by delta rho, delta phi, delta rho, delta theta, delta phi. And the volume increment is, as we've seen, rho I star squared sine theta k star times our delta rho, delta phi, the delta theta. Said that backwards again, but you know what I mean here. So our delta m is this expression. This is all from preceding clips. And our ultimate goal, remember, was to find the moment of inertia of the Earth. Now the Earth is spherically symmetric. Its mass distribution is distributed according to the approximate spherical distribution, as we've already seen. So that the moment of inertia about any axis through the center is going to be the same as any other. So moment of inertia about any axis through the center is the same as through any other axis. Through the center. Not sure you can see that whole statement, but I think you get the idea. Okay. So we can choose any axis we wish. We can choose the z-axis as our axis of rotation. We could choose the x, or we could choose the y. Well, the x or the y-axis as our axis of rotation. We're going to want to find mr squared for our increment. So we're going to want to find the expression for this, where our Ri star is our distance from the axis of rotation, and I think I shouldn't have written it as Ri star squared, because that could easily be confused with the cylindrical coordinate. And as far as we know right now, we could be using any axis for our axis of rotation. That would be appropriate if we use the z-axis. That is, in fact, what we're going to choose to do, but let's explore the other possibilities first. So I'm going to be a little vague. I've changed that Ri star squared to radius. We're trying to get mr squared. I don't want to use just r because that is a cylindrical or a polar coordinate. Just reminding us at this point that we want to add up the mass times distance squared, where our mass times radius squared, where radius excuse me, radius means the distance of our mass from the axis of rotation. And we want to think then about what is our distance, our radius, our distance from the axis of rotation. Which axis do we want to use? We're probably going to want to use one of the coordinate axes, but we have to make a decision about which one is the most reasonable or the easiest to use in this situation. So let's see. If we use the z-axis as our axis of rotation, how far is it from the z-axis to our sample point? Well, that distance is actually going to be the same as this distance, which is, in terms of rho, theta, and phi, is going to be rho sine phi. In other words, for this particular increment, our distance from the z-axis is rho I star sine phi k star. That's going to be fairly easy to calculate. So one choice is to use the z-axis as our axis of rotation, and for the radius use rho I star phi sine of phi k star. Another option would be to use the y-axis as our axis of rotation. Then our distance from the axis would be the distance from this point to this point. Okay, now that distance isn't something that's all that easy to calculate in spherical coordinates. We'd have to get an expression for this distance, and then we'd have a right triangle and so forth. Alternatively, this distance and our distance here. This distance would be rho cosine phi. This distance would be rho sine phi cosine theta. Be kind of complicated. If we use the x-axis as our axis of if we use the x-axis as our axis of rotation, we'd have a triangle from here to here to here and back to here. One of those sides would be, it turns out, rho sine phi, which would be this distance times the cosine of theta, and it's probably not something we want to get involved in. So having thought through the various possibilities, we end up choosing the z-axis as the axis of rotation. Could have chosen any line through the origin, wouldn't even have to be an axis. I mean, wouldn't even have to be one of our coordinate axes, but the z-axis is, in fact, our simplest possible choice. In this case, then, how far are we from the z-axis? Well, let's just draw it again and draw a little picture out to a point. Here's our z-axis. From the z-axis out to this point is going to be parallel to the line down in the xy or our theta plane from the origin to the projection of the point. And this distance, remember, this is our angle phi, this is rho, so this distance here, or this distance here, is just rho sine phi. Now we're talking about the specific sample point, so that our contribution to the moment of inertia from our ijk interval is going to equal our delta m for the ijk interval, multiplied then by rho sub I star sine of phi k star, where our delta mij is this expression. Well, when we multiply rho I star sine phi k star by this expression, what do we get? Our sine phi k star will multiply our sine phi k star, giving us a square of this factor, and our rho I star will multiply this rho I star squared, giving us a rho I star cubed. So this becomes, what, 12 minus 9 rho I star divided by r times rho I star now cubed times the sine squared of phi k star times delta rho delta theta delta phi. We can sum these up. Again, we're going to be partitioning the same intervals we did before. Rho from 0 to r, theta from 0 to 2 pi, phi from 0 to pi. So this is going to approach just the integral, triple integral, from 0 to pi, 0 to 2 pi, and 0 to big R of 12 minus 9 rho over r times rho cubed sine squared phi d rho d theta d phi. We see that once again we're just going to be integrating a polynomial, in this case 12 rho to the third minus 9 rho to the fourth over r. That's going to be an easy integral. The limits on our integrals are all constants, so we're not going to have any complication from that. And we're going to have to integrate the sine squared of phi, which is something we've seen how to do. And that integral just goes from 0 to pi. So having set up the integral for our moment of inertia, we have a pretty clear path to complete the integral and get our expression. We'll do that in the next clip.